4. Cluster sampling, multi-stage sampling. Under this method, random selection is made of primary, intermediate and final units from a given population. There are several stages in which the sampling process is carried out. Initially, random samples of first stage units are selected. As the second step, from the first stage units, second stage units are selected randomly. Further stages are added as required. Illustration: if we want a sample of 5,000 secondary school students of Kerala state, we can take the educational districts of Kerala as the first units. After selecting required number of districts, say 7, randomly, sub-districts of each district constitute the second units. Required number of sub-districts can be randomly selected, say 20. Secondary schools constitute the third-level units and some schools are selected randomly from the sub-districts selected. From these schools, standards can be randomly selected and finally the classes are selected which constitute the final sample. Merits. 1. There is flexibility in sampling. It enables existing divisions and subdivisions of the population to be used as units at various stages in a large area can be covered with more accuracy. 2. If the population is infinite or very large, i.e. when it is difficult to list all the population units, cluster sampling can be used. Demerits. A multi-stage sample is in general less accurate than a sample containing the same number of final stage units selected through other methods. Major non-probability sampling methods are 1. Judgment purposive sampling. 2. Quota sampling and 3. Convenience sampling. 1. Judgment sampling. In this method, the choice of sample items depends exclusively on the judgment of the investigator. The investigator includes those items in the sample, which he thinks are most typical of the universe population with regard to the characteristics under consideration. Merits. 1. When the population contains only a small number of sampling units, random selection may miss more important elements, whereas judgment sample would certainly include them in the sample. 2. In solving everyday business problems and making public policy decisions, executives and public officials are pressed for time and cannot wait for probability sampling designs. Then judgment sampling is the only practical solution. Demerits. 1. This method is not scientific. It may be influenced by the personal bias of the investigator. 2. If the investigator has enough knowledge about the population and has good judgment, the resulting sample will be representative of the population, otherwise, the inferences based on the sample will be erroneous. 3. There is no objective method to determine the size of sampling error. 2. Quota sampling. In quota sampling, quotas are set up according to some specified characteristics such as so many in each of several income groups, so many in each age, etc. Each interviewer is asked to interview a certain number of persons which constitute his quota. Within the quotas, the selection of sample items depends on personal judgment. Merits. 1. Quota sampling is used in public opinion studies. 2. It may provide satisfactory results if the interviewers are trained and follow the instructions closely. Demerits. 1. There is possibility of personal bias which may affect the results. 2. The sample may not be a true representation of the population. 3. Convenience sampling. A convenience sample or accidental sample is obtained by selecting convenient population units. Here the sample elements are selected neither by probability method nor judgment but by convenience. Merits. Convenience sampling can be used in pilot studies. Demerits. There is a high probability of bias and will not be a representation of the population. Sampling error. The results derived from a sample study may not be exactly equal to the true value in the population. That is, sampling gives rise to certain errors known as sampling errors or sampling fluctuations. Sampling error may be biased or unbiased. Biased errors arise from any bias in selection, estimation, etc. Unbiased errors arise due to chance differences between the members of population included in the sample and those not included. Non-sampling errors. When a complete enumeration of units in the universe is made, one would expect that it would give rise to data free from errors. But it is difficult to completely avoid errors of observation or ascertainment while processing data. Tabulation errors may be committed affecting the final results. Errors arising in this manner are termed as non-sampling errors. Thus, the data obtained in an investigation by complete enumeration, although free from sampling error, would still be subject to non-sampling errors, whereas the results of a sample survey would be subject to sampling error as well as non-sampling error. Module -3. Probability and expected value. Object. Module. Error. When a complete. Merits. Convenience sample. Sampling error. The results derived from a sample study may not be exactly equal to the true value in the population. That is, sampling gives rise to certain errors known as sampling errors or sampling fluctuations. Sampling error may be biased or unbiased. Biased errors arise from any bias in selection, estimation, etc. Unbiased errors arise due to chance differences between the members of population included in the sample and those not included. Non-sampling errors. When a complete enumeration of units in the universe is made, one would expect that it would give rise to data free from errors. But it is difficult to completely avoid errors of observation or ascertainment while processing data. Tabulation errors may be committed affecting the final results. Errors arising in this manner are termed as non-sampling errors. Thus, the data obtained in an investigation by complete enumeration, although free from sampling error, would still be subject to non-sampling errors, whereas the results of a sample survey would be subject to sampling error as well as non-sampling error. Module -3. Probability and expected value. Objectives. 1. To know the meaning and definition of probability. 2. To develop understanding about the theorems of probability. The word probability is very much used in general conversation, but the theory of probability has its origin in the games of chance related to gambling such as throwing a die, tossing a coin, drawing cards from a pack of cards etc. Girolamo Cardano 1501-76, an Italian mathematician, is considered as the first man who wrote a book on probability. An attempt to quantify probability was made by the Italian mathematician Galileo, 1564–1642. A systematic and scientific foundation of mathematical theory of probability was laid in mid-17th century by the French mathematicians Pascal, 1623–62, and Pierre de Fermat, 1601–65. Jacques Bernoulli, 1654–1705, through his treatise on probability has contributed much to the theory of probability. The doctrine of chances, the work of de Moivre, 1667–1754, was a remarkable step in the field of probability theory. Works of Thomas Bayes, 1702–61, and Pierre-Simon Laplace, 1749–1827, gave a classical approach to probability. R. A. Fisher, 1890–1962, and R. V. Mises, 1883–1953, introduced empirical approach to probability through the concept of sample space. Modern approach to probability was given by Chebyshev, 1821–94, a Markov, 1856–1922, etc. Thus, starting with games of chance, probability has become one of the tools of statistics. A basic knowledge of probability is essential to deal with statistics. Definition of probability. The probability of a given event is an expression of likelihood or chance of occurrence of an event. An event means the outcome of an experiment. The concept of probability of an event is explained differently by different schools of thought. Classical a priori probability. The classical approach to probability is the oldest and simplest one. The basic assumption of classical theory is that the outcomes of a random experiment are equally likely. Laplace defined probability as the ratio of the number of favorable cases to the total number of equally likely cases. According to this definition, probability of an event AP A equals number of favorable cases. Total number of equally likely cases. Limitations. 1. Not applicable when a simple enumeration of equally likely cases is not possible, e.g. possibility of rain or no rain, is not always equally likely. 2. Real-life situations are often unlikely and disorderly, and hence it will be difficult to apply classical probability concept. 2. Relative frequency theory of probability, empirical. In this approach, probability of an event is the limit of the relative frequency as the number of observation increases indefinitely. If an event occurs, times out of n, its relative frequency is a(n), the value which is approached by a(n) when n becomes infinity is called the limit of the relative frequency. That is, p a equals lim a(n). n infinity. Limitations. Though this approach is useful in practice, has difficulties from a mathematical point of view. Definition of probability. The probability of a given event is an expression of likelihood or chance of occurrence of an event. An event means the outcome of an experiment. The concept of probability of an event is explained differently by different schools of thought. Classical a priori probability. The classical approach to probability is the oldest and simplest one. The basic assumption of classical theory is that the outcomes of a random experiment are equally likely. Laplace defined probability as the ratio of the number of favorable cases to the total number of equally likely cases. According to this definition, probability of an event AP A equals number of favorable cases. Total number of equally likely cases. Limitations. 1. Not applicable when a simple enumeration of equally likely cases is not possible, e.g. possibility of rain or no rain, is not always equally likely. 2. Real-life situations are often unlikely and disorderly, and hence it will be difficult to apply classical probability concept. 2. Relative frequency theory of probability, empirical. In this approach, probability of an event is the limit of the relative frequency as the number of observation increases indefinitely. If an event occurs, times out of n, its relative frequency is a(n), the value which is approached by a(n) when n becomes infinity is called the limit of the relative frequency. That is, p a equals lim a(n). n infinity. Limitations. Though this approach is useful in practice, has difficulties from a mathematical point of view since an actual limiting number may not really exist. 3. Subjective approach to probability. The subjective probability is defined as the probability assigned to an event by an individual based on whatever evidence is available. Here probabilities are based on the beliefs of the person making the probability statement. For example, if a teacher is finding the probability of a particular student to be highest in the board examination, he may assign a value between 0 and 1 according to his belief for possible occurrence. His belief will be based on the factors like past academic performance of the student, view of colleagues, attendance record, etc. Limitations. The personalistic approach, being very broad and highly flexible, permits probability assignment to events for which there may be no objective data or for which there may be a combination of objectives and subjective data, and is very useful in business decision-making. But if at most care is not taken, the decisions made may be misleading. 4. Axiomatic approach to probability. The Russian mathematician A. N. Kolmogorov introduced the axiomatic approach to probability in 1933, which introduces probability as a set function. There is no precise definition of probability in this approach, but certain axioms, postulates are given on which probability can be calculated. The whole field of probability theory for finite sample spaces, the set of all possible outcomes of a random experiment is called sample space of the experiment denoted as S, is based on the following three axioms. 1. The probability of an event ranges from 0 to 1. If the event cannot occur, the probability will be 0, and if it is certain, the probability is 1. 2. The probability of the entire sample space is 1, i.e. P(S) equals 1. 3. If A and B are mutually exclusive disjoint events, then the probability of occurrence of either A or B, PAUB equals PA plus PB. Calculation of probability. There are certain terms which are essential for an understanding of the calculation of probability. They are 1. Experiment and events. An act, which can be repeated under some given conditions, is known as an experiment. A random experiment is one whose results depend on chance. Example, tossing of a coin, throwing of dice, etc. The results of a random experiment are called outcomes. In tossing of a coin, the outcomes are head H or tail T, while in the case of dice, the outcomes are 1, 2, 3, 4, 5 or 6. In these experiments all the possible outcomes are known in advance, and none of the outcomes can be predicted with certainty. While tossing a coin, one knows that possible outcomes are H and T, but no one can be certain that the outcome of a particular toss is H or T. These possible outcomes of a random experiment are called events. An event whose occurrence is inevitable when a certain random experiment is performed is called a certain or sure event, and that can never occur is called an impossible event. In the experiment, tossing of a coin, the outcomes H and T are sure events, whereas coin showing not H or T, i.e. with edges upward, can be considered as an impossible event. An event which may or may not occur while performing a certain random experiment is known as a random event. Occurrence of H is a random event in the above random experiment of tossing of a coin. 2. Mutually exclusive events. Two events are said to be mutually exclusive, incompatible, if both cannot happen simultaneously in a single trial or the occurrence of any one of them precludes the occurrence of the other. E.g., when a coin is tossed, the occurrence of head H precludes the occurrence of tail T. Both of them cannot occur at the same time in a single toss. Hence these two events are mutually exclusive. If A and B are two mutually exclusive events, probability of occurrence of both of A and B. PAB equals 0. 3 events A, B, C are mutually exclusive only if either A or B or C can occur. 3. Independent events. Two or more events are independent when the outcome of one does not affect and is not affected by other. E.g., if a coin is tossed twice, the outcome of first toss is not affecting or affected by the outcome of the second. That is, suppose in the first toss, a tail is obtained, then the second toss may result either T or H, not influenced by the first outcome. T similarly, the first outcome is not influenced by the outcome of the second. Dependent events are those in which the occurrence or non-occurrence of one event in any one trial affects the probability of other events in other trials. If a card is drawn from a pack of playing cards and is not replaced, this will alter the probability that the second card drawn is, say, an ace. 4. Equally likely events. Events are mutually likely when one does not occur more often than the others. Example, if an unbiased coin is tossed, head and tail may be expected to be observed approximately the same number of times in the long run. But if the coin is biased, one should not expect each face to appear exactly the same number of times. 5. Simple and compound events. In simple event we consider the probability of the happening or not happening of single events. In the case of finding the probability of drawing a white ball from a set of 20 black balls and 15 white balls, the event is simple as only one outcome is expected. In compound events, the joint occurrences of two or more events are considered. If two successive draws of 2 balls are made from a set of 20 black balls and 15 white balls, the probability of getting 2 white balls in the first draw and 2 black balls in the second draw, in this case we are dealing with a compound event as there are two single events occurring at the same time. 6. Exhaustive events. Events are said to be exhaustive if their totality includes all the possible outcomes of a random experiment. E.g., in the case of throwing a dice, the possible events are showing the face with number 1, 2, 3, 4, 5 or 6. Thus the exhaustive number of cases is 6. 7. Complementary events. An event A is said to be the complementary event of B, and vice versa, if A and B are mutually exclusive and exhaustive. E.g., when a dice is thrown, occurrence of an odd number A and occurrence of an even number B are complementary events. Here are results in 1, 3, 5 and B in 2, 4, 6. If these two are combined, the whole sample space has occurred and one prevents the occurrence of the other. Theorems of probability. Important theorems of probability are 1. The addition theorem and 2. The multiplication theorem. The addition theorem states that if two events A and B are mutually exclusive, the probability of the occurrence of either A or B is the sum of the individual probability of A and B. I.e., if A and B are mutually exclusive or disjoint events, P A or B equals P A U B equals P A plus P B. This theorem can be extended to more mutually exclusive events A, B and C. P A U B U C equals P A plus P B plus P C. Proof: if an event A can happen A 1 times and B A 2 times, and the total number of outcomes being in P A equals a 1, P B equals a 2. N number of times either A or B can happen is a 1 plus a 2. Thus probability of A or B is P A or B equals a 1 plus a 2 equals a 1 plus a 2. NNNIE. P A U B equals P A plus P B. E.g., one card is drawn from a standard pack of 52. What is the probability that the card selected is either a heart or a spade? equals the events that the card selected is a heart, and the card selected is a spade are mutually exclusive as only one card is selected and the card selected is heart and spade, is not possible. P A equals 13 P B equals 13. 52 P A or B equals P A plus P B. Equals 13 plus 13 equals 26 equals 1. 52. If the events are not mutually exclusive, that is, if there is a probability of occurrence of both the events, then P A or B equals P A U B equals P A plus P B P A B. I.e. in the case of events which are not mutually exclusive, the probability of occurrence of A or B is the probability of A plus probability of B, probability of A and B. E.g., what is the probability of selecting either a queen or a heart from a standard pack of cards? The events that occurrence of a heart and the occurrence of a queen are not mutually exclusive as both can occur at a time. I.e., the card selected may be a queen of hearts. Thus P A or B equals P queen or hearts. Equals P A plus P B P A intersection B. Equals P queen plus P hearts P queen of hearts. Equals 4 plus 13 1 equals 17 to 1 equals 16 equals 4. 52 This theorem can be extended as P A or B or C equals P A plus P B plus P C P A B P B C P A C plus P A B C. Multiplication theorem. If two events A and B are independent, probability that they both will occur is the product of their individual probability. That is, P A and B equals P A x P B. Extending this theorem to more events. P A B C equals P A, P B, P C. Proof. If an event A can happen n1 ways out of which A1 are favorable for A and B can happen n2 ways out of which A2 are favorable for B, then a combination of successful event in both cases will be A1x A2 from a total of n1x n2 cases. Thus P A B equals A1 A2 equals A1x A2. N1 N2 N1 N2 equals P A. P B. Conditional probability and Bayes' theorem. If two events A and B are dependent, i.e. when B can occur only when A is known to have occurred or vice versa, then the conditional probability of a given B P A B equals P A B. P B and probability of B given A P B A equals P A B. P A. Proof. Suppose A1 is the number of cases for the simultaneous happening of A and B out of A1 plus A2 cases in which B can happen with or without happening of A. P A B equals A1 N equals P A B. A1 plus A2 A1 plus A2 N P B. The multiplication theorem can be also expressed as P A B equals P B P A B. P A B equals P A P B A. P A B C equals P A x P B A x P C A B. E.g. a bag contains 20 black and 15 white balls. Two balls are drawn at random one after the other without replacement. Find the probability that both balls drawn are black. Let A be the event of getting a black in the first draw and B be that in the second draw, then P A equals 20. 35 P B A equals P getting a black ball provided that black ball is taken in the first draw equals 19. 34 P A and B equals P both balls are black. Equals P B A 19. P A 34. Equals 20 equals 19 x 7 equals 133. 353444136. This concept of conditional probability is used to predict the probability of one event on the basis of the information about the occurrence of another event. Using this conditional probability, Bayes' theorem determines the probability that a particular effect was due to a specific cause. This theorem is named after the British mathematician Rev. Thomas Bayes 1702-61. Bayes' theorem can be expressed symbolically as P I B equals P B I. P I. N area summation P B A J P A J. Where A1, A2, A3, I, and are n mutually exclusive and collectively exhaustive events. B is another event with P B does not equal 0. For two mutually exclusive and exhaustive events A1 and A2, B another event which intersects events A1 and A2, see figure. S. P A1 B equals P A1 B. P B P A2 B equals P A2 B. P B P B equals P A1 and B plus P A2 and B P A1 and B equals P B A1. P A1. Conditional probability. P A2 and B equals P B A2. P A2 P A1 B equals P B A1. P A1. P B A1. P A1 plus P B A2. P A2 A1 A2. B. If the event exponential function. In mathematics, the exponential function is a unique real function which maps 0 to 1 and has a derivative equal to its value. The exponential of a variable is denoted r, with the two notations used interchangeably. It is called exponential because its argument can be seen as an exponent to which a constant number e approximately equals 2.718, the base, is raised. There are several other definitions of the exponential function, which are all equivalent although being of very different nature. Exponential functions with bases 2 and 1/2. The exponential function converts sums to products. It maps the additive identity 0 to the multiplicative identity 1, and the exponential of a sum is equal to the product of separate exponentials. Its inverse function, the natural logarithm, or, converts products to sums. Other functions of the general form, with base, are also commonly called exponential functions, and share the property of converting addition to multiplication. Where these two meanings might be confused, the exponential function of base is occasionally called the natural exponential function, matching the name natural logarithm. The generalization of the standard exponent notation to arbitrary real numbers as exponents is usually formally defined in terms of the exponential and natural logarithm functions as the natural base is the unique base satisfying the criterion that the exponential function's derivative equals its value, which simplifies definitions and eliminates extraneous constants when using exponential functions in calculus. Quantities which change over time in proportion to their value, for example the balance of a bank account bearing compound interest, the size of a bacterial population, the temperature of an object relative to its environment, or the amount of a radioactive substance, can be modeled using functions of the form, also sometimes called exponential functions. These quantities undergo exponential growth if is positive or exponential decay if is negative. The exponential function can be generalized to accept a complex number as its argument. This reveals a relation between the multiplication of complex numbers and rotation in the Euclidean plane. Euler's formula: the exponential of an imaginary number is a point on the complex unit circle at angle from the real axis. The identities of trigonometry can thus be translated into identities involving exponentials of imaginary quantities. The complex function is a conformal map from an infinite strip of the complex plane, which periodically repeats in the imaginary direction onto the whole complex plane except for. The exponential function can be even further generalized to accept other types of arguments, such as matrices and elements of Lie algebras. Some old texts refer to the exponential function as the antilogarithm. 1. The graph of is upward sloping, and increases faster as x increases. 2. The graph always lies above the x-axis, but becomes arbitrarily close to it for large negative x, thus, the x-axis is a horizontal asymptote. The equation means that the slope of the tangent to the graph at each point is equal to its height, its y-coordinate, at that point. Exponential. The natural exponential function along part of the real axis. General information. General definition. Domain, codomain and image domain. Image. Specific values at 0, 1. Value at 1e. Specific features. Fixed point minus wn minus 1, 4. Related functions. Reciprocal. Inverse natural logarithm, complex logarithm. Derivative. Antiderivative. Series definition. Graph. There are several different definitions of the exponential function, which are all equivalent, although of very different nature. One of the simplest definitions is, the exponential function is a unique differentiable function that equals its derivative, and takes the value 1 for the value 0 of its variable. This conceptual definition requires a uniqueness proof and an existence proof, but it allows an easy derivation of the main properties of the exponential function. Uniqueness: if an or two functions satisfying the above definition, then the derivative of is 0 everywhere by the quotient rule. It follows that is constant, and this constant is 1 since the exponential function is the inverse function of the natural logarithm. The inverse function theorem implies that the natural logarithm has an inverse function that satisfies the above definition. This is a first proof of existence. Therefore, one has, for every real number and every positive real number, the exponential function in blue and the sum of the first n plus 1 terms of its power series in red. Taylor series. Definitions and fundamental properties. The exponential function is the sum of a power series, 3, 4. Whereas the factorial of n the product of the n first positive integers. This series is absolutely convergent for every per the ratio test. So, the derivative of the sum can be computed by term-by-term derivation, and this shows that the sum of the series satisfies the above definition. This is a second existence proof, and shows, as a byproduct, that the exponential function is defined for every, and is everywhere the sum of its Maclaurin series. The exponential satisfies the functional equation. This results from the uniqueness in the fact that the function satisfies the above definition. It can be proved that a function that satisfies this functional equation is the exponential function if its derivative at 0 is 1 and the function is either continuous or monotonic. Positiveness: for every, one has, since the functional equation implies. It results that the exponential function is positive since, if one would have for some, the intermediate value theorem would imply the existence of some such that. It results also that the exponential function is monotonically increasing. Extension of exponentiation to positive real bases: let b be a positive real number. The exponential function and the natural logarithm being the inverse each of the other, one has if n is an integer, the functional equation of the logarithm implies. Since the rightmost expression is defined if n is any real number, this allows defining for every positive real number b and every real number x. In particular, if b is the Euler's number, one has inverse function, and thus. This shows the equivalence of the two notations for the exponential function. The exponential function is the limit 5, 4. Where it takes only integer values, otherwise, the exponentiation would require the exponential function to be defined by continuity of the logarithm. This can be proved by taking logarithms and proving. For example, with Taylor's theorem. General exponential functions. Sometimes exponential function is used as the name for all functions with the argument somewhere in the exponent of an exponentiation, as well as 6. This has serious disadvantages. 7. In this section, the name exponential function will be used for functions obeying one of the following 3 equivalent conditions. For all pairs of arguments with the same difference in the domain are mapped into pairs of values with the same ratio in the codomain 8, 9, 10, 11. For all, the value of is independent of the value of sometimes. The rate constant 12, 13 is independent of 14. Expressions for exponential functions. The value of argument, real or complex, of an exponential function can be expressed with as dash, opening parenthesis, comma, closing parenthesis, dash, dash. Exponential functions mapping quantities instead of numbers are usually expressed as quantity being the unit in which quantity, mostly time, is measured, resulting in a dimensionless exponent. Hierarchy of types. Exponential functions with quantities as elements of domain and codomain, e.g. the lilies in the pond, growing with the same factor during time intervals of equal length. In applications in empirical sciences, notations within are commonly used. Exponential growth can be modeled by a function with its doubling time. An exponential decay can be modeled by a function with its half-life. Exponential functions with domain, see section complex exponential, below. Exponential functions obeying for all, changing additions into multiplications, the opposite of the main property of logarithmic functions, changing multiplications into additions, equivalent with the condition. Their expressions have dot. Exponential functions obeying, the function is identical with its own derivative. Their expressions have the unique exponential function obeying as well as is called the exponential function, or sometimes the natural exponential function. Symbol. Its expressions have two meanings of base. For exponential functions, the independent value of is called the base of the function. 15 while in expressions. And caret, the value of the first element is called the base of the exponentiation. Example, the exponential function has base, while the expression has base and exponent. Properties. The Euler number is connected with every exponential function. When argument increases by, changes by factor 4. Dot. The graph of an exponential function in polar coordinates is a logarithmic spiral or equiangular spiral, 16, 17. In a logarithmic spiral with pitch angle 45, the length of a radius vector increases by a factor when the polar angle increases by 1 radian. And by the factor at a 180 switch. See, logarithmic spiral, section properties, rotating, scaling. An exponential function is determined by 2 points. With, positive, and determine the exponential function. 18. The red curve is the exponential function. The black horizontal lines show where it crosses the green vertical lines. The exponential function arises whenever a quantity grows or decays at a rate proportional to its current value. One such situation is continuously compounded interest, and in fact it was this observation that led Jacob Bernoulli in 1683-19 to the number now known as E. Later, in 1697, Johann Bernoulli studied the calculus of the exponential function. 19. If a principal amount of 1 earns interest at an annual rate of x compounded monthly, then the interest earned each month is x. 12 times the current value, so each month the total value is multiplied by 1 plus x. 12 and the value at the end of the year is 1 plus x. 12, 12. If instead interest is compounded daily, this becomes 1 plus x. 365, 365. Letting the number of time intervals per year grow without bound leads to the limit definition of the exponential function. First given by Leonhard Euler. 5. This is one of a number of characterizations of the exponential function, others involve series or differential equations. From any of these definitions it can be shown that e minus x is the reciprocal of x. For example, from the differential equation definition, xe minus x equals 1 when x equals 0 and its derivative using the product rule is xe minus x equals 0 for all x, so xe minus x equals 1 for all x. From any of these definitions it can be shown that the exponential function obeys the basic exponentiation identity. For example, from the power series definition, expanded by the binomial. Overview. Theorem. This justifies the exponential notation x for express x. The derivative rate of change of the exponential function is the exponential function itself. More generally, a function with a rate of change proportional to the function itself is expressible in terms of the exponential function. This derivative property leads to exponential growth or exponential decay. The exponential function extends to an entire function on the complex plane. Euler's formula relates its values at purely imaginary arguments to trigonometric functions. The exponential function also has analogues for which the argument is a matrix, or even an element of a Banach algebra or a Lie algebra. Derivatives and differential equations. The derivative of the exponential function is equal to the value of the function. From any point P on the curve blue let a tangent line red and a vertical line green with height h be drawn, forming a right triangle with a base b on the x-axis. Since the slope of the red tangent line, the derivative at P is equal to the ratio of the triangle's height to the triangle's base, rise over run, and the derivative is equal to the value of the function, h must be equal to the ratio of h to b. Therefore, the base b must always be 1. The importance of the exponential function in mathematics and the sciences stems mainly from its property as a unique function which is equal to its derivative and is equal to 1 when x equals 0. That is, functions of the form ax for constant are the only functions that are equal to their derivative by the Picard-Lindelof theorem. Other ways of saying the same thing include: the slope of the graph at any point is the height of the function at that point. The rate of increase of the function at x is equal to the value of the function at x. The function solves the differential equation y equals y. Express as a fixed point of derivative is a linear operator on function space. If a variable's growth or decay rate is proportional to its size, as is the case in unlimited population growth, see Malthusian catastrophe, continuously compounded interest, or radioactive decay, then the variable can be written as a constant times an exponential function of time. More generally, for any real constant k, a function f, our right pointing arrow r satisfies if and only if for some constant a. The constant k is called the decay constant, disintegration constant, 20, rate constant, 21, or transformation constant, 22. Furthermore, for any differentiable function f, we find, by the chain rule, continued fractions for x. A continued fraction for x can be obtained via an identity of Euler. The following generalized continued fraction for EZ converges more quickly, 23. Or, by applying the substitution z equals x, y, with a special case for z equals 2. This formula also converges, though more slowly, for z greater than 2. For example, the exponential function e caret z plotted in the complex plane from -2 to I to 2 plus 2i. Complex exponential. A complex plot of, with the argument represented by varying hue. The transition from dark to light colors shows that is increasing only to the right. The periodic horizontal bands corresponding to the same hue indicate that is periodic in the imaginary part of. As in the real case, the exponential function can be defined on the complex plane in several equivalent forms. The most common definition of the complex exponential function parallels the power series definition for real arguments, where the real variable is replaced by a complex one. Alternatively, the complex exponential function may be defined by modeling the limit definition for real arguments, but with the real variable replaced by a complex one. For the power series definition, termwise multiplication of two copies of this power series in the Cauchy sense, permitted by Merton's theorem, shows that the defining multiplicative property of exponential functions continues to hold for all complex arguments. The definition of the complex exponential function in turn leads to the appropriate definitions extending the trigonometric functions to complex arguments. In particular, when z equals at t real, the series definition yields the expansion in this expansion. The rearrangement of the terms into real and imaginary parts is justified by the absolute convergence of the series. The real and imaginary parts of the above expression in fact correspond to the series expansions of cos t and sin t, respectively. This correspondence provides motivation for defining cosine and sine for all complex arguments in terms of the equivalent power series. 24. For all the functions express, cos, and sin defined have infinite radii of convergence by the ratio test and are therefore entire functions, that is, holomorphic on. The range of the exponential function is. While the ranges of the complex sine and cosine functions are both in its entirety, in accord with Picard's theorem, which asserts that the range of a non-constant entire function is either all of, or excluding one lacunary value. These definitions for the exponential and trigonometric functions lead trivially to Euler's formula. We could alternatively define the complex exponential function based on this relationship. If z equals x plus iy, where x and y are both real, then we could define its exponential as where express, cos, and sin on the right-hand side of the definition sine are to be interpreted as functions of a real variable, previously defined by other means. 25. 4. The relationship holds, so that for real n maps the real line mod 2 pi to the unit circle in the complex plane. Moreover, going from to, the curve defined by traces a segment of the unit circle of length. Starting from z equals 1 in the complex plane and going counterclockwise. Based on these observations and the fact that the measure of an angle in radians is the arc length on the unit circle subtended by the angle, it is easy to see that, restricted to real arguments, the sine and cosine functions as defined above coincide with the sine and cosine functions as introduced in elementary mathematics via geometric notions. The complex exponential function is periodic with period 2 pi I and holds for all. When its domain is extended from the real line to the complex plane, the exponential function retains the following properties. For all, extending the natural logarithm to complex arguments yields the complex logarithm log z, which is a multivalued function. We can then define a more general exponentiation. For all complex numbers c and w, this is also a multivalued function, even when z is real. This distinction is problematic, as the multivalued functions log z and zw are easily confused with their single-valued equivalents when substituting a real number for z. The rule about multiplying exponents for the case of positive real numbers must be modified in a multivalued context. EZW does not equal EZW, but rather EZW equals E, Z plus 2 ni pi, W multivalued over integers NC. Failure of power and logarithm identities for more about problems with combining powers. The exponential function maps any line in the complex plane to a logarithmic spiral in the complex plane with the center at the origin. Two special cases exist. When the original line is parallel to the real axis, the resulting spiral never closes in on itself. When the original line is parallel to the imaginary axis, the resulting spiral is a circle of some radius. 3D plots of real part, imaginary part, and modulus of the exponential function. Z equals re x plus iy, z equals im, x plus iy, z equals x plus iy. Considering the complex exponential function is a function involving 4 real variables. The graph of the exponential function is a two-dimensional surface curving through 4 dimensions. Starting with a color-coded portion of the domain, the following are depictions of the graph as variously projected into 2 or 3 dimensions. Graphs of the complex exponential function. The third and fourth images show how the graph in the second image extends into one of the other 2 dimensions not shown in the second image. The third image shows the graph extended along the real axis. It shows the graph as a surface of revolution about the axis of the graph of the real exponential function, producing a horn or funnel shape. The fourth image shows the graph extended along the imaginary axis. It shows that the graph's surface for positive and negative values doesn't really meet along the negative real axis, but instead forms a spiral surface about the axis. Because its values have been extended to plus or minus 2 pi, this image also better depicts the 2 pi periodicity in the imaginary value. The power series definition of the exponential function makes sense for square matrices, for which the function is called the matrix exponential, and more generally in any unit-Banach algebra B. In this setting, E0 equals 1, and x is invertible with inverse E minus x for any x in B. If xy equals yx, then x plus y equals xey, but this identity can fail for non-commuting x and y. Some alternative definitions lead to the same function. For instance, x can be defined as, or x can be defined as fx1, where fx, our right pointing arrow b is the solution to the differential equation. dfx dtt equals xfxt with initial condition fx0 equals 1, it follows that fxt equals etx for every t in R. Given a Lie group G and its associated Lie algebra, the exponential map is a map rightwards arrow from bar G satisfying similar properties. In fact, since R is the Lie algebra of the Lie group of all positive real numbers under multiplication, the ordinary exponential function for real arguments is a special case of the Lie algebra situation. Similarly, since the Lie group GLn, R of invertible n times n matrices has as Lie algebra Mn, R the space of all n times n matrices, the exponential function for square matrices is a special case of the Lie algebra exponential map. The identity can fail for Lie algebra elements x and y that do not commute. The Baker-Campbell-Hausdorff formula supplies the necessary correction terms. Matrices and Banach algebras. Lie algebras. Transcendency. The function Ez is not in the rational function ring, it is not the quotient of two polynomials with complex coefficients. If A1, and are distinct complex numbers, then A1z, A-nz are linearly independent over, and hence Ez is transcendental over. Computation. The Taylor series definition above is generally efficient for computing an approximation of. However, when computing near the argument, the result will be close to 1, and computing the value of the difference with floating point arithmetic may lead to the loss of possibly all significant figures, producing a large relative error, possibly even a meaningless result. Following a proposal by William Kahan, it may thus be useful to have a dedicated routine, often called EXPM1, which computes x-1 directly, bypassing computation of x. For example, one may use the Taylor series. This was first implemented in 1979 in the Hewlett-Packard HP41C calculator, and provided by several calculators, 2627 operating systems, for example Berkeley Unix 4.3 Bahamian Sense, 28 computer algebra systems, and programming languages, for example C99. 29. In addition to base E, the IEEE 754-2008 standard defines similar exponential functions near 0 for base 2 and 10, and a similar approach has been used for the logarithm, CLNP1. NB1, an identity in terms of the hyperbolic tangent. Gives a high precision value for small values of x on systems that do not implement EXPM1x. See also Carlot's exponential, a characteristic P analog. In mathematics, the logarithm to base b is the inverse function of exponentiation with base b. That means that the logarithm of a number x to the base b is the exponent to which b must be raised to produce x. For example, since 1000 equals 103, the logarithm base of 1000 is 3, or log 10 1000 equals 3. The logarithm of x to base b is denoted as log b x, or without parentheses, log b x. When the base is clear from the context or is irrelevant, it is sometimes written log x. Plots of logarithm functions, with three commonly used bases. The special points log b equals 1 are indicated by dotted lines, and all curves intersect in log b1 equals 0. The logarithm base 10 is called the decimal or common logarithm and is commonly used in science and engineering. The natural logarithm has the number e approximately equals 2.718 as its base. Its use is widespread in mathematics and physics because of its very simple derivative. The binary logarithm uses base 2 and is frequently used in computer science. Logarithms were introduced by John Napier in 1614 as a means of simplifying calculations. 1. They were rapidly adopted by navigators, scientists, engineers, surveyors, and others to perform high-accuracy computations more easily. Using logarithm tables, tedious multi-digit multiplication steps can be replaced by table lookups and simpler addition. This is possible because the logarithm of a product is the sum of the logarithms of the factors. Provided that b, x and y are all positive and b does not equal 1. The slide rule, also based on logarithms, allows quick calculations without tables, but at lower precision. The present-day notion of logarithms comes from Leonhard Euler, who connected them to the exponential function in the 18th century, and who also introduced the letter e as the base of natural logarithms. 2. Logarithmic scales reduce wide-ranging quantities to smaller scopes. For example, the decibel dB is a unit used to express ratio as logarithms, mostly for signal power and amplitude, of which sound pressure is a common example. In chemistry, pH is a logarithmic measure for the acidity of an aqueous solution. Logarithms are commonplace in scientific formulae, and in measurements of the complexity of algorithms and of geometric objects called fractals. They help to describe frequency ratios of musical intervals, appear in formulas counting prime numbers or approximating factorials, and form some models in psychophysics, and can aid in forensic accounting. The concept of logarithm as the inverse of exponentiation extends to other mathematical structures as well. However, in general settings, the logarithm tends to be a multi-valued function. For example, the complex logarithm is the multi-valued inverse of the complex exponential function. Similarly, the discrete logarithm is the multi-valued inverse of the exponential function in finite groups. It has uses in public key cryptography. Motivation. The graph of the logarithm base 2 crosses this axis at x equals 1 and passes through the points 2, 1, 4, 2, and 8, 3 depicting, e.g., log 2, 8 equals 3 and 23 equals 8. The graph gets arbitrarily close to the y-axis, but does not meet it. Addition, multiplication, and exponentiation are three of the most fundamental arithmetic operations. The inverse of addition is subtraction, and the inverse of multiplication is division. Similarly, a logarithm is the inverse operation of exponentiation. Exponentiation is when a number b, the base, is raised to a certain power y, the exponent, to give a value x. This is denoted, for example, raising 2 to the power of 3 gives 8. The logarithm of base b is the inverse operation that provides the output y from the input x. That is equivalent to if b is a positive real number. If b is not a positive real number, both exponentiation and logarithm can be defined but may take several values, which makes definitions much more complicated. One of the main historical motivations of introducing logarithms is the formula, by which tables of logarithms allow multiplication and division to be reduced to addition and subtraction, a great aid to calculations before the invention of computers. Definition. Given a positive real number b such that b does not equal 1, the logarithm of a positive real number x with respect to base b, nb1, is the exponent by which b must be raised to yield x. In other words, the logarithm of x to base b is the unique real number y such that 3. The logarithm is denoted, log bx, pronounced as, the logarithm of x to base b, the base b logarithm of x, or most commonly, the log, base b, of x. An equivalent and more succinct definition is that the function log b is the inverse function to the function. Examples. Log 216 equals 4, since 24 equals 2 times 2 times 2 times 2 equals 16. Logarithms can also be negative, since log 10,150 is approximately 2.176, which lies between 2 and 3, just as 150 lies between 102 equals 100 and 103 equals 1000. For any base b, log bb equals 1 and log b1 equals 0, since b1 equals b and b0 equals 1, respectively. Logarithmic identities. Several important formulas, sometimes called logarithmic identities or logarithmic laws, relate logarithms to one another. 4. Product, quotient, power, and root. The logarithm of a product is the sum of the logarithms of the numbers being multiplied. The logarithm of the ratio of two numbers is the difference of the logarithms. The logarithm of the pth power of a number is p times the logarithm of the number itself. The logarithm of a pth root is the logarithm of the number divided by p. The following table lists these identities with examples. Each of the identities can be derived after substitution of the logarithm definitions or in the left-hand sides. Product, quotient, power, and root identities of logarithms. Identity formula example. Product quotient power. Root. Change of base. The logarithm log bx can be computed from the logarithms of x and b with respect to an arbitrary base k using the following formula, nb2. Typical scientific calculators calculate the logarithms to bases 10 and e. 5 logarithms with respect to any base b can be determined using either of these two logarithms by the previous formula. Given a number x and its logarithm y equals log bx to an unknown base b, the base is given by, which can be seen from taking the defining equation to the power of. Overlaid graphs of the logarithm for bases 1, 2, 2, and e. Among all choices for the base, 3 are particularly common. These are b equals 10, b equals e, the irrational mathematical constant e approximately equals 2.718288183, and b equals 2, the binary logarithm. In mathematical analysis, the logarithm base e is widespread because of analytical properties explained below. On the other hand, base 10 logarithms, the common logarithm, are easy to use for manual calculations in the decimal number system, 6. Thus, log 10x is related to the number of decimal digits of a positive integer x. The number of digits is the smallest integer strictly bigger than log 10x. 7 for example, log 10 5986 is approximately 3.78. The next integer above it is 4, which is the number of digits of 5986. Both the natural logarithm and the binary logarithm are used in information theory, corresponding to the use of nats or bits as the fundamental units of information, respectively. 8 binary logarithms are also used in computer science, where the binary system is ubiquitous, in music theory, where a pitch ratio of 2 the octave is ubiquitous and the number of cents between any two pitches is a scaled version of the binary logarithm, or log 2 times 1200, of the pitch ratio, that is, 100 cents per semitone in conventional equal temperament, or equivalently the log base 21 1200s, and in photography rescaled base 2 logarithms are used to measure exposure values, light levels, exposure times, lens apertures, and film speeds in, stops. 9. The abbreviation log x is often used when the intended base can be inferred based on the context or discipline, or when the base is indeterminate or immaterial. Common logarithms base 10, historically used in logarithm tables and slide rules, are a basic tool for measurement and computation in many areas of science and engineering. In these contexts log x still often means the particular bases. Base 10 logarithm. 10 in mathematics log x usually means to the natural logarithm base e. 11, 12 in computer science and information theory, log often refers to binary logarithms base 2. The following table lists common notations for logarithms to these bases. The ISO notation column lists designations suggested by the International Organization for Standardization. 13. Base B name for log bx ISO notation other notations. 2 binary logarithm LBX 14 LDX log x LGX 15 log 2x east natural logarithm lane x NB3 log x log x 10 common logarithm LGX log x log 10 xb logarithm to base B log bx. History. The history of logarithms in 17th century Europe saw the discovery of a new function that extended the realm of analysis beyond the scope of algebraic methods. The method of logarithms was publicly propounded by John Napier in 1614, in a book titled Mirafici Logarithmorum Canonis Descriptio, Description of the Wonderful Canon of Logarithms. 1920 Prior to Napier's invention, there had been other techniques of similar scopes, such as the prosophoresis or the use of tables of progressions, extensively developed by Joost Bürgi around 1600. 2122 Napier coined the term for logarithm in Middle Latin, logarithmus, literally meaning ratio number, derived from the Greek logos proportion, ratio, word, plus arithmos number. The common logarithm of a number is the index of that power of 10 which equals the number. 23 Speaking of a number as requiring so many figures is a rough allusion to common logarithm, and was referred to by Archimedes as the order of a number. 24 The first real logarithms were heuristic methods to turn multiplication into addition, thus facilitating rapid computation. Some of these methods used tables derived from trigonometric identities. 25 Such methods are called prosophoresis. Invention of the function now known as the natural logarithm began as an attempt to perform a quadrature of a rectangular hyperbola by Grégoire de Saint Vincent, a Belgian Jesuit residing in Prague. Archimedes had written the quadrature of the parabola in the 3rd century BC, but a quadrature for the hyperbola eluded all efforts until Saint Vincent published his results in 1647. The relation that the logarithm provides between a geometric progression in its argument and an arithmetic progression of values, prompted A. de Sarasa to make the connection of Saint Vincent's quadrature and the tradition of logarithms in prosophoresis, leading to the term, hyperbolic logarithm, a synonym for natural logarithm. Soon the new function was appreciated by Christian Huygens, and James Gregory. The notation log y was adopted by Leibniz in 1675, 26 and the next year he connected it to the integral. Before Euler developed his modern conception of complex natural logarithms, Roger Coates had a nearly equivalent result when he showed in 1714 that 27 logarithm tables, slide rules, and historical applications. The 1797 Encyclopaedia Britannica explanation of logarithms. By simplifying difficult calculations before calculators and computers became available, logarithms contributed to the advance of science, especially astronomy. They were critical to advances in surveying, celestial navigation, and other domains. Pierre-Simon Laplace called logarithms, an admirable artifice which, by reducing to a few days the labor of many months, doubles the life of the astronomer, and spares him the errors and disgust inseparable from long calculations. 28. As the function f(x) equals bx is the inverse function of log bx, it has been called an antilogarithm. 29. Nowadays, this function is more commonly called an exponential function. Log tables. A key tool that enabled the practical use of logarithms was the table of logarithms. 30. The first such table was compiled by Henry Briggs in 1617, immediately after Napier's invention but with the innovation of using 10 as the base. Briggs' first table contained the common logarithms of all integers in the range from 1 to 1000, with a precision of 14 digits. Subsequently, tables with increasing scope were written. These tables listed the values of log 10x for any number x in a certain range, at a certain precision. Base 10 logarithms were universally used for computation, hence the name common logarithm, since numbers that differ by factors of 10 have logarithms that differ by integers. The common logarithm of x can be separated into an integer part and a fractional part, known as the characteristic and mantissa. Tables of logarithms need only include the mantissa, as the characteristic can be easily determined by counting digits from the decimal point. 31. The characteristic of 10x is 1 plus the characteristic of x, and their mantissas are the same. Thus using a 3-digit log table, the logarithm of 3542 is approximated by. Greater accuracy can be obtained by interpolation. The value of 10x can be determined by reverse lookup in the same table, since the logarithm is a monotonic function. Computations. The product and quotient of two positive numbers c and d were routinely calculated as the sum and difference of their logarithms. The product CD or quotient CD came from looking up the antilogarithm of the sum or difference, via the same table. And for manual calculations that demand any appreciable precision, performing the lookups of the two logarithms, calculating their sum or difference, and looking up the antilogarithm is much faster than performing the multiplication by earlier methods such as prosopharesis, which relies on trigonometric identities. Calculations of powers and roots are reduced to multiplications or divisions and lookups by and. Trigonometric calculations were facilitated by tables that contained the common logarithms of trigonometric functions. Slide rules. Another critical application was the slide rule, a pair of logarithmically divided scales used for calculation. The non-sliding logarithmic scale, Gunter's rule, was invented shortly after Napier's invention. William Outard enhanced it to create the slide rule, a pair of logarithmic scales movable with respect to each other. Numbers are placed on sliding scales at distances proportional to the differences between their logarithms. Sliding the upper scale appropriately amounts to mechanically adding logarithms, as illustrated here. Schematic depiction of a slide rule. Starting from 2 on the lower scale, add the distance to 3 on the upper scale to reach the product 6. The slide rule works because it is marked such that the distance from 1 to x is proportional to the logarithm of x. For example, adding the distance from 1 to 2 on the lower scale to the distance from 1 to 3 on the upper scale yields a product of 6, which is read off at the lower part. The slide rule was an essential calculating tool for engineers and scientists until the 1970s, because it allows, at the expense of precision, much faster computation than techniques based on tables. 32. Analytic properties. A deeper study of logarithms requires the concept of a function. A function is a rule that, given one number, produces another number. 33. An example is the function producing the xth power of b from any real number x, where the base b is a fixed number. This function is written as f(x) equals bx. When b is positive and unequal to 1, we show below that f is invertible when considered as a function from the reals to the positive reals. Existence. Let b be a positive real number not equal to 1 and let f(x) equals bx. It is a standard result in real analysis that any continuous strictly monotonic function is bijective between its domain and range. This fact follows from the intermediate value theorem. 34. Now, f is strictly increasing for b greater than 1 or strictly decreasing for 0 less than b less than 1. 35 is continuous, has domain, and has range. Therefore, f is a bijection from 2. In other words, for each positive real number y, there is exactly one real number x such that we let denote the inverse of f. That is, log by is the unique real number x such that This function is called the base b logarithm function or logarithmic function or just logarithm. Characterization by the product formula. The function log bx can also be essentially characterized by the product formula. More precisely, the logarithm to any base b greater than 1 is the only increasing function f from the positive reals to the reals satisfying fb equals 1 and 36. Graph of the logarithm function. The graph of the logarithm function log bx blue is obtained by reflecting the graph of the function bx red at the diagonal line x equals y. As discussed above, the function log b is the inverse to the exponential function. Therefore, their graphs correspond to each other upon exchanging the x and the y coordinates or upon reflection at the diagonal line x equals y, as shown at the right. A point t, u equals bt on the graph of f yields a point u, t equals log bu on the graph of the logarithm and vice versa. As a consequence, log bx diverges to infinity gets bigger than any given number if x grows to infinity, provided that b is greater than 1. In that case, log bx is an increasing function. For b less than 1, log bx tends to minus infinity instead. When x approaches 0, log bx goes to minus infinity for b greater than 1 plus infinity for b less than 1, respectively. Derivative and antiderivative. The graph of the natural logarithm green and its tangent at x equals 1.5 black. Analytic properties of functions pass to their inverses. 34. Thus, as f(x) equals bx is a continuous and differentiable function, says log by. Roughly, a continuous function is differentiable if its graph has no sharp corners. Moreover, as the derivative of f(x) evaluates to lane bx by the properties of the exponential function, the chain rule implies that the derivative of log bx is given by 35-37. That is, the slope of the tangent touching the graph of the base b logarithm at the point x, log bx equals 1 x lane b. The derivative of lane x is 1x. This implies that lane x is a unique antiderivative of 1x that has the value 0 for x equals 1. It is this very simple formula that motivated to qualify as natural, the natural logarithm. This is also one of the main reasons of the importance of the constant e. The derivative with a generalized functional argument f(x) is the quotient at the right-hand side is called the logarithmic derivative of f. Computing f(x) by means of the derivative of lane f(x) is known as logarithmic differentiation. 38. The antiderivative of the natural logarithm lane x is 39. Related formulas, such as antiderivatives of logarithms to other bases, can be derived from this equation using the change of bases. 40. Integral representation of the natural logarithm. The natural logarithm of t is the shaded area underneath the graph of the function f(x) equals 1x. The natural logarithm of t can be defined as the definite integral This definition has the advantage that it does not rely on the exponential function or any trigonometric functions. The definition is in terms of an integral of a simple reciprocal. As an integral, lane t equals the area between the x-axis and the graph of the function 1x, ranging from x equals 1 to x equals t. This is a consequence of the fundamental theorem of calculus and the fact that the derivative of lane x is 1x. Product and power logarithm formulas can be derived from this definition. 41. For example, the product formula lane 2 equals lane t plus lane u is deduced as the equality 1 splits the integral into two parts, while the equality 2 is a change of variable w equals xt. In the illustration below, the splitting corresponds to dividing the area into the yellow and blue parts. Rescaling the left-hand blue area vertically by the factor t and shrinking it by the same factor horizontally does not change its size. Moving it appropriately, the area fits the graph of the function f(x) equals 1x again. Therefore, the left-hand blue area, which is the integral of f(x) from t to 2 is the same as the integral from 1 to u. This justifies the equality 2 with a more geometric proof. A visual proof of the product formula of the natural logarithm. The power formula lane tr equals r lane t may be derived in a similar way. The second equality uses a change of variables integration by substitution w equals x1 r. The sum over the reciprocals of natural numbers is called the harmonic series. It is closely tied to the natural logarithm. As n tends to infinity, the difference converges, i.e. gets arbitrarily close, to a number known as the Euler-Mascheroni constant gamma equals 0.5772. This relation aids in analyzing the performance of algorithms such as quicksort. 42. Transcendence of the logarithm. Real numbers that are not algebraic are called transcendental. 43. For example, pi near such numbers, but is not. Almost all real numbers are transcendental. The logarithm is an example of a transcendental function. The Gelfand-Schneider theorem asserts that logarithms usually take transcendental, i.e., difficult, values. 44. Calculation. The logarithm keys log for base 10 and ln for base e on a TI-83 plus graphing calculator. Logarithms are easy to compute in some cases, such as log 10 1000 equals 3. In general, logarithms can be calculated using power series or the arithmetic geometric mean, or be retrieved from a pre-calculated logarithm table that provides a fixed precision. 45-46 Newton's method, an iterative method to solve equations approximately, can also be used to calculate the logarithm, because its inverse function, the exponential function, can be computed efficiently. 47 Using lookup tables, Cordic-like methods can be used to compute logarithms by using only the operations of addition and bit shifts. 48-49 Moreover, the binary logarithm algorithm calculates LB(x) recursively, based on repeated squarings of x, taking advantage of the relation. Power series. Taylor series. The Taylor series of lane z, centered at z equals 1. The animation shows the first 10 approximations along with the 99th and 100th. The approximations do not converge beyond a distance of 1 from the center. For any real number z that satisfies 0 less than z is less than or equal to 2, the following formula holds, NB450. Equating the function lane z to this infinite sum series is shorthand for saying that the function can be approximated to a more and more accurate value by the following expressions known as partial sums. For example, with z equals 1.5 the third approximation yields 0.4167, which is about 0.011 greater than lane 1.5 equals 0.405465, and the ninth approximation yields 0.40553, which is only about 0.0001 greater. The nth partial sum can approximate lane z with arbitrary precision, provided the number of summands n is large enough. In elementary calculus, the series is said to converge to the function lane z, and the function is the limit of the series. It is the Taylor series of the natural logarithm at z equals 1. The Taylor series of lane z provides a particularly useful approximation to lane 1 plus z when z is small, z less than 1, since then. For example, with z equals 0.1 the first order approximation gives lane 1.1 approximately equals 0.1, which is less than 5% off the correct value 0.0953. Inverse hyperbolic tangent. Another series is based on the inverse hyperbolic tangent function. For any real number z greater than 0, NB550, using sigma notation, this is also written as. This series can be derived from the above Taylor series. It converges quicker than the Taylor series, especially if z is close to 1. For example, for z equals 1.5, the first three terms of the second series approximate lane 1.5 with an error of about 3 times 10 minus 6. The quick convergence for z close to 1 can be taken advantage of in the following way, given a low accuracy approximation y approximately equals lane z and putting the logarithm of z is. The better the initial approximation y is, the closer a is to 1, so its logarithm can be calculated efficiently. A can be calculated using the exponential series, which converges quickly provided y is not too large. Calculating the logarithm of larger z can be reduced to smaller values of z by writing z equals a 10b, so that lane z equals lane a plus b lane 10. A closely related method can be used to compute the logarithm of integers. Putting in the above series, it follows that if the logarithm of a large integer n is known, then this series yields a fast converging series for log n plus 1 with a rate of convergence of arithmetic geometric mean approximation. The arithmetic geometric mean yields high-precision approximations of the natural logarithm. Sasaki and Kanata showed in 1982 that it was particularly fast for precisions between 400 and 1000 decimal places, while Taylor series methods were typically faster when less precision was needed. in their work lane x is approximated to a precision of 2 minus p, or p precise bits by the following formula due to Carl Friedrich Gauss 5152. Here m, x, y denotes the arithmetic geometric mean of x and y. It is obtained by repeatedly calculating the average x plus y, 2 arithmetic mean, and geometric mean of x and y, then let those two numbers become the next x and y. The two numbers quickly converge to a common limit, which is the value of m, x, y. M is chosen such that, to ensure the required precision, a larger m makes the m, x, y calculation take more steps. The initial x and y are farther apart, so it takes more steps to converge but gives more precision. The constants pi and lane 2 can be calculated with quickly converging series. Feynman's algorithm.